Okay, so this is section 8-1. This is recording number 2. Okay, so here we go. I always urge you to read the objectives. I don't think it's necessary for me to read that to you. So read the objectives, make sure you understand what it is we're trying to do on all of these sections. All right, so I think we discussed this already, did we not? Yes. Okay. Now I'm counting on you guys to read this stuff, right? I mean, obviously I can't read word for word everything. You guys have got to be reading this as well. Okay, so here we go. This is always true. Every hypothesis testing situation begins with this, the statement of a hypothesis. Now, what the heck is a hypothesis? A hypothesis is a conjecture. I wouldn't call it a guess, but it has to be an educated guess. You know, it's something that you think, well, this might be true. Maybe, let me just pick an example that everybody can relate to. Certain cereals, okay? Wheaties cereals. Does Wheaties cereal really make you feel better? Does Wheaties cereal help you lose weight? Something of that sort, okay? So that's your conjecture. You have a reason to believe it. And you are making this hypothesis, and it may or may not be true. Okay, so that's what we're talking about right here. Okay, there are two types of statistical hypotheses for every situation. You have a null hypothesis, Here's the symbol for it, H sub 0 or H sub naught. Naught is spelled N-A-U-G-H-T, so H sub naught. That's a statistical hypothesis, may or may not be true. It's a statistical hypothesis that says, hey, there's no difference. There's no difference between a parameter and a specific value, or that there is no difference between two parameters. So what does that mean? What that means is, if my theory is that if you eat your Wheaties, you can do more push-ups than average, okay? And the average is 10 push-ups. But if you eat your Wheaties for 6 months, you can do more than 10, okay? The alternative, the null hypothesis says, hey, there's no difference. If the average number of push-ups that you can do is 10, after you eat your Wheaties, the average number is going to be 10. Okay, the alternative hypothesis, and we denote that, our symbol is H sub 1. That's a hypothesis that states, hey, there's a difference. There's a difference between the parameter and a specific value, or that there's a difference between two parameters. So I'm saying, hey, you know what? You eat your Wheaties, and you are going to be able to do more push-ups. Okay, so that's the alternative hypothesis. Okay, so here we go. Here's some examples. If you like these examples, get them memorized so you really truly understand them if this is what you're interested in. I always have nurses in the class, so maybe you'd be interested in this. If some of you are interested in getting your BSN and you want to become some sort of a health officer, this would be the typical type of thing that you would be interested in learning about, okay, or doing research about. So here we go. The medical researcher wants to find out, does this new medication have any undesirable side effects? And one of the things that he's concerned about, he or she is concerned about, is the pulse rate. So will the pulse rate increase? Will it decrease? Will it remain unchanged after a patient takes the medication? So my advice is always be able to clearly state what is the random variable. The random variable here is pulse rate. Okay? The researcher knows that the mean pulse rate for the population under study is 82 beats per minute. So what we're saying here is, hey, we've done these surveys a million times, and we know that on average, the population that I'm concerned about has a mean pulse rate of 82 beats per minute. It doesn't matter what the population is, right? It could be, you know, young people, it could be old people, whatever population that you're looking at, that particular pulse rate, on average, the mean pulse rate is 82 beats per minute. So the hypothesis for this situation is H sub 0 or H naught, the null hypothesis is that mu equals 82. So what we're saying is, hey, that's what it is. That when you take your sample, nothing's going to change. And then the alternative hypothesis is, no, 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 you're wrong. It is going to change. When I do this experiment, when I give all these people the medication, the mean is going to change. It's not going to be equal to 82. So that's what he says right here. The null hypothesis says that the mean will remain unchanged. The alternative hypothesis states that it will be different. This is called a two-tailed test, and we'll define that later on. But the intuition is two-tailed because the possible side effects can be more or less. It can raise it or it can decrease it. Okay, so the same idea applies to all of these ones here. This is one is talking about the automobile battery, that the lifetime of the automobile battery is greater than 36, and so forth. Okay, so I'm going to let you read those. I hope you have read those. Okay, so a right tail test and a left tail test. Okay, now this author likes to always have tables that you can refer to, and that's okay, I guess, but in my opinion, you're better off to just understand the material and develop your own intuition so you don't have to rely on a table. In a moment of stress, as a human being, you're going to forget these tables. You're going to forget these little algorithms here. So my recommendation is truly understand the material, and then you can figure it out for yourself, and it takes a second to figure it out and follow your intuition. Okay, so in this, now this is important. In this book, the null hypothesis is always stated using the equals sign. Okay, and he's justifying that his justification is that in most professional journals, and when we test the null hypothesis, the assumption is made that the mean, proportion, or standard deviation, whatever it is that we're looking at. See, this is an example of the mean. We could also be testing proportion or standard deviation. It's typical that what we say is, the null hypothesis is that the mean is equal to whatever it happens to be. So in this, let's use my favorite example, which is here. The average, the mean for the population is 82. So that's what we typically will do. Mu is equal to 82, or mu is equal to some number. And we have some reason to believe that that number is correct, okay? All right. So when you conduct this study, you're going to be looking for evidence to support a claim. So let's suppose your claim is, hey, I think that taking this medication makes your pulse rate go up. That's my claim. So that's the alternative hypothesis. And we typically use these guys right here. We'll say, well, it's less than, it's greater than, or it's not equal to. So typically that's what you're going to see. And because it's a research environment, oftentimes the alternative hypothesis is sometimes called the research hypothesis. So think about it in our current context of the COVID virus. What would be a research hypothesis? The research hypothesis would be that if you take this medication, this anti-malarial medication, the mean number of days that you are sick is going to decrease. The null hypothesis is that it does not decrease. It's exactly the same as whatever it is. So if the average mean, if the mean number of days that people are sick is 10, H sub 0 would be mu is equal to 10. You are testing the hypothesis that a certain medication reduces the number of days that you are sick. The alternative hypothesis, the H sub 1, would be that mu is less than 10. Okay, so here's some typical phrases that we use. I'll let you read those, but that's kind of the typical type of thing that you'll see, okay? All right, so let's take a look at these. These are worth taking a quick gander at. You're studying gambling, okay? She thinks that the people that gamble spend more than $30 a day, okay? All right, so here's one. We say, okay, the null hypothesis is there is no difference. It's exactly the same, okay, as hold on one second. Okay, so here's a little bit of a nuance here. She thinks that you spend more than $30 a day. So the null hypothesis is $30, and the reason why is because if you're going to make this hypothesis, if you're going to say, hey, I claim that it's more than $30, well, you've got to prove it. And it's got to be a statistically significant difference from 30. It has to be significantly higher than 30. So that's why it's expressed this way. And so we're not comparing a sample necessarily to a population in a strict sense of the word. Okay, number 2 here is a little closer to what we were talking about before. We're talking about police officers whose spouses work in law enforcement have a lower score on a work stress questionnaire. So in other words, you think, well, you know what? If you're a police officer and your spouse is a police officer, your spouse understands what you're going through, so you're going to have less work stress. So the average score of the population might be 120. So the null hypothesis is that mu is equal to 120. Your claim, your alternative hypothesis, your H sub 1 is that no, the mean is less than 120 for this sample that I'm picking. I'm picking these police officers who have a spouse that works in law enforcement. Okay, so I'll let you do the next one by yourself. Okay. All right, so how do we do this? You state the hypothesis. You say, okay, here's my hypothesis. This is exactly what I'm testing. I'm testing that Wheaties makes you able to do more push-ups. This medication raises your heart rate. This medication lowers your heart rate, whatever it happens to be. Well, then what you do is you choose the correct statistical test, which we're going to see in a few minutes here. How do you pick the right statistical test? Is it the Z-test, the T-test? What is it? You choose an appropriate level of significance. Well, the level of significance is how certain do you want to be? Do you only want to be wrong by random chance 10% of the time? How about 5% of the time? Well, if you're talking about medications where somebody's going to die if you're making a mistake, well, you want it to be pretty darn significant. You want it to be where I'm only wrong like 1% of the time. So the type of a statistical test that you're doing, or what kind of an experiment you're doing, will dictate what the level of significance is. Again, if you are talking about someone dying if you're wrong, well, then you want it to be very, very certain. If you're talking about, well, the parts won't fit, or or how many push-ups can you do, well, really, does anybody care, right? So you can be wrong maybe 10% of the time. Okay. Okay, now this next paragraph here is very significant. In my book, my printed book, I made some notes here and I highlighted it. I want you to read this very, very carefully, okay? When you're taking samples of a specific size, when you take them from a population, the means of those samples, those X bars, they are a random variable. This is the central limit theorem. And they will vary about the population mean, right? We learned that in the central limit theorem section. That was section 6-3. The distribution of those X bars will be approximately normal if the sample size is 30 or more, okay? So what it's saying is that even if the null hypothesis is true, even if when you take those samples out of the population, using the pulse rates as an example, so even if the null hypothesis is true, if there is no significant difference, if h sub 0 is that mu is equal to some number, okay, so there's no change. That's the null hypothesis. Okay, that's what we had up here. That's situation A. Null hypothesis is that mu is equal to 82. Okay, so I'm almost out of time, so let me stop this recording right here, and when we resume, we're going to be talking about this paragraph that I just told you was so important. I may have to be a little bit redundant. Okay, so that's the end of this recording.